In search of soil.
So, Mike, thanks for taking the time to join me today. You're currently CEO of the company JOYN Bio, and it's a really interesting company. At the core of it, what is JOYN setting out to do?
I'd say our core mission is to answer a question that is, from our perspective, very important to agricultural innovation. And that is, can you take beneficial microbes and using the advanced technologies of synthetic biology, can you engineer those microbes in an optimized way so that they're delivering solutions to growers that have the same performance and the same consistency as traits and chemicals do? And we're just trying to answer that question. Can you do that? Can you actually engineer that beneficial microbe so that it provides performance that is unprecedented from a microbial solution perspective?
When you think about that question and even asking that question, how possible is it? Obviously, you guys must think it's possible if you have a company setting out to do it. Is this like a 10 out of 10 extremely hard problem to crack? We wouldn't be there now without the technology we have, or maybe we even need more technology to get there. Or is it more like a five? It's doable with the tech we have, the knowledge we have, but there's just a lot of work that's going to have to go into making it happen. How hard is this to actually achieve?
So I think there's a couple ways to look at it. I think when we were proposing this company slash concept inside of Bayer almost three and a half years ago, it was referred to as a moonshot. So it wasn't a Mars shot, but it also wasn't going across country. So we talked about it as a moonshot, and this was fairly specific to our nitrogen fixation project, right? So, is it difficult? Yes. There's really, a couple big hurdles that you have to get over. One is that historically, synthetic biology has been used and has been done in a contained environment. And those microbes that are engineered in that contained environment are engineered to produce a product, produce a metabolite, produce a fragrance, produce a specialty chemical that's then isolated away. And everything that happens is inside that container, right, with that engineered microbe. So that's done. What we need to do is engineer that microbe and grow it up, but it has to function in the field. It has to function on a seed. It has to function for a grower out in the environment. And so that means we have to find a whole new set of chassis or host microbes that have very different properties than E. coli or yeast or some of the traditional synthetic biology hosts that are used. So that's one big hurdle. Can you find those hosts or chassis, and will they go out and survive in the field? Will they go out and colonize the plant as the delivery vehicle, right? The second piece is, on a totally different scale or perspective, is if you do that and they work really well, can you get them registered, and what's the consumer acceptance of a GMO or an engineered microbe? Can you get over that hurdle? We believe the answer to that is a strong yes. We believe it's connected directly to benefit, so that if we provide a solution to something as critical as reducing fertilizer levels with cereal crops, or if we could provide a new solution for Asian soybean rust or citrus greening, some of these big problems in ag, we believe people will give it a chance. And then it's just a question of, can we develop the safety data packages that support being able to use these products in the environment. So these are big hurdles, if you will, or reasons why somebody like Bayer would probably not take this on in their internal crop science. It's too risky, right? And that's why they set up the joint venture with Ginkgo and are doing this. And we've been funded to do this as an independent company because we can take more risk and do it at arm's length. We can be more entrepreneurial, if we're successful, then one of the folks that we would go back to with that solution is Bayer. So it's a very cool model from their perspective, and it's a really creative way for Bayer to drive innovation for transformative but high risk projects versus doing it internally internally where the R&D has to be I would just say has to have a higher probability of success or has to have fewer hurdles.
When you think about that first problem that you brought up, you have to create a microbe that can survive outside of the lab. It has to survive in the wild. Is there an analogy of that out there? Not necessarily in ag, but anywhere where science is engineering microbes that are surviving in the wild to perform a function that they weren't naturally derived to do?
I would say that we're really just on the cusp of looking at that. So I think we're clearly driving that question or driving that from an agricultural perspective. There are people who are looking at it in terms of the human gut microbiome and potential solutions there. There's people that are looking at it from an animal health perspective. There's people who are going to look at it in the context of bioremediation. So can you take a microbe that already is pretty good at chewing up oil from an oil spill, and can you engineer it so that it's 10 times or 100 times more effective? Or can you engineer a microbe so that it can bioremediate heavy metals and this type? So yeah, I think but I think we're at a pretty early, we're at such an early stage. And I think a lot of this, it's interesting if you go back over the last 5-6 years uh, and look at what scientific topics have been the most published, have had the most articles. Number one is CRISPR-Cas, right? Hands down. Number two is the microbiome. And this whole concept of understanding the microbiome, its relationship to human health, its relationship to animal health, and in our case, its relationship to plant health and soil health, and the plant microbiome and the soil microbiome, just understanding how integral these microbes are to the everyday health and production and longevity, of these plants. This is a whole new area. People are just starting to understand this, and it's exciting to see. Not only is it on the plant side, but look at the amount of effort that's going on say the human side, recognizing the human microbiome and its role in a lot of different diseases and human health.
Right, right. How, in terms of difficulty and this moonshot, the too risky for Bayer to take on, how much of it is it actually being hard, and how much of it is our understanding or lack of understanding of microbiology? I hear this a lot, and I don't know if it's true. And you can tell me. I mean, you're in the field that a lot of things when it gets into soil microbiology, we don't understand very much of how those things function down there in the soil. And I'm sure it's the same in the human gut. Is that accurate? And is that we're trying to build off of a non-robust knowledge base going forward? Is that part of the problem, or is this just hard to begin with? But we know enough at the foundation. It's just hard.
I think it's I think it's hard for two reasons. One is I think the complexity can be overwhelming. If you think about, I don't know I think if you take a tablespoon of soil, there's like 4 billion microbes in there. If you take the sheer complexity of the microbiome, whether it's on the human skin, whether it's in a human gut, whether it's on a plant, or whether it's in a tablespoon of soil, there's just a complexity there that at this stage is somewhat overwhelming. What has made it suddenly approachable, if you will, are the explosion of sequencing and genomic tools in a high throughput way, along with the software and the algorithms to process all that information that are emerging from the synthetic biology field. And so even though there might be 1 million or 1 billion of these, our ability to sort out and look at these is starting to emerge. But it's absolutely true that we're just at the just because of the sheer complexity of it, we're at the very tip of the iceberg of trying to understand it, very early stages. Now, if you isolate and take a single microbe, so you take the complexity from what's in a soil sample to let's isolate a single microbe. Now you've got something that's actually fairly easy to work with from an engineering perspective. Easier to work with than a plant, much easier to work with than an animal or a human from an engineering. So understanding pathways, introducing genes or adjusting pathways. So optimizing certain aspects of that microbe for a specific purpose. At the individual microbe level, it suddenly has become doable, if you will. So I think it's that contrast, right, between incredible complexity out there in the soil, but if you get to that single microbe, you actually have something that today's genomic tools can actually work with and sequence and understand fairly effectively.
So when you set out about to do this and you isolate the single microbe, there's two potential paths I see here. Is one, you look for a microbe that can survive out in the wild and is receptive to taking on the traits that you want it to take on. In this case, it's nitrogen fixation. So you take that existing microbe and you build nitrogen fixation onto it. Another pathway could be you take a nitrogen fixing microbe, rhizobia, and instead of having it bond with just certain plants, you now essentially open up its filter or its lens, and it can now bond with other plants that aren't just legumes. Is there one path that is more likely, or is there a third path that I'm not seeing?
No, I think in the case of the nitrogen fixation, I think in simple terms, those are sort of the two paths that you have. Um, what we what we if you think about what the characteristics are of what we call a chassis or host microbe, some of the ones you mentioned, it needs to be stable in the environment. It needs to be tractable or easily engineered. But the other critical one for us is it needs to colonize and associate with the plant. And so if you think about the ideal um, nitrogen fixation product for corn, okay, it would be applied to the corn as a seed treatment, right? That's by far the most effective way to apply a new solution to a crop like that, where you've already got a lot of the farmer has already invested heavily in acquiring that corn seed from either Bayer or Corteva, two of them, right? That you get it, and it's already been optimized from a genetic standpoint, from a hybrid corn breeding standpoint. And then if you can put a seed treatment on it that provides additional benefit, in this case, a nitrogen fixing microbe, if you can put it on when that grower goes to plant the corn, which he's going to do, that microbe, that nitrogen fixation solution is already on the seed. Now, what that microbe has to do then is, as that seed germinates, as it's in the soil, as it goes into the soil, and as it germinates, ideally you want a microbe that associates with the entire corn plant through its entire life cycle, right? And it will grow and populate that plant, colonize it in a symbiotic way. So, you might say, well, are there microbes that do that? And the answer is absolutely, right? There are microbes who form symbiotic relationships, and they get something that they need from the corn and vice versa, right? And that microbe can be providing things, signaling or providing things back to the corn plant. So what we're looking for, one of the things we're looking for ideally is sort of a combination of what you mentioned, which is start with some microbes that already have some of the nitrogen fixing machinery in them. Make some adjustments to it, because one of the things that happens in those microbes is that they have mechanisms that when there's plenty of nitrogen around, they shut off. And so what you want that nitrogen fixing microbe to do is not shut off its nitrogen fixation, but actually ramp it up. And so you actually have to do some engineering to make that happen. The other part of this, and I mentioned life cycle of the corn. If you're a corn grower, biggest benefit of a product like this, of a new solution like this, would be if it can deliver the nitrogen in the second half of its life cycle, because that's when it takes up most of its night. If you think about a corn, it's the corn plant, it's growing up, it's in that second half of its growth period that it's actually producing the corn, and that's when it uses about 78. It needs about 70 to 80% of its nitrogen. However, if you think about, well, when did the fertilizer get applied? Way back before when it was planted, right? So that's why they have to put on. That's one reason why the levels of synthetic fertilizer are as high as they are, because they have to try to last in the soil through that whole growing season. So if we can get a microbe that fixes the nitrogen, colonizes the corn plant via a seed treatment, right? Then and it goes through the lifetime, it can be fixing and delivering nitrogen in that second half of the growth cycle. And that's ideal for the grower, because now he doesn't have to rely on putting so much on in the beginning, and he doesn't have to worry about having to go back out if he needs to and reapplying nitrogen to make sure he's got the right amount of nutrient there to optimize his yield or his productivity per acre.
I know just from doing reading, the nitrogen fixation process in a plant's very carbon intensive. In order to do that, given that, do you have to modify the carbon flow of a corn plant so it feeds those microbes what they need to do that conversion? I don't think you can get just a free lunch, right? Where they fix nitrogen, they're not taking anything back. So do you need to change something within the corn to now deliver surplus carbon in the form of sugars to really get that pump going?
I think it's a good question. To be honest, I don't think we know exactly how it's going to work in a successful. So one of the things we're looking at is exactly that. Are there microbes that are out there that have that relationship already in place, or that can, in theory, can form that symbiotic relationship with the corn? And so part of the studies and assays that we do is identifying what we call endophytic bacteria, ones that are inside, will exist inside the plant, and not just on the roots or not just in the soil, but can they actually populate the entire plant, that actually will be getting nutrients or getting something beneficial from that corn plant, right? Such that they're actually incented, or they actually do colonize over an extended period of weeks and even a couple of months. That's what we're looking for. And so for us, because this is new, because people haven't really gone out there and tried to find chassis or hosts that do the colonization and also can be reasonably engineered in the lab, a big part of our initial work is identifying as many of these potential hosts or chassis as we can.
If we zoom out here and we just think microbiology or just general biology, is there a reason why nitrogen fixing bacteria form relationships with legumes, but they don't with other plants? In other words, why did some plants evolve not to have this relationship?
I what I've heard. I'm not not an expert in this area of plant evolution. But my understanding is that in the case of, say, soybeans or peanuts and some of the legumes that do fix nitrogen and actually fix it with these rhizobia microbes, they actually fix it with the nodules in their roots at a level where they almost don't need fertilizer. Matter of fact, people will actually rotate soybeans with corn, because after growing soybeans for a year, there's actually more nitrogen in the soil than before you planted them. So they actually are nitrogen positive, if you will. Somewhere in this whole thing, as soybeans were evolving, they must have been in an environment that was nitrogen poor. And so it was an evolutionary thing where the ones that actually started to develop these nodules and these nitrogen fixing microbes would outcompete and would eventually be the norm, if you will. versus soybeans that were in a soybean environment where you had depleted nitrogen. You didn't have enough nitrogen there. Evolution is gonna favor the ones that can actually fix the nitrogen, actually evolve that way. For whatever reason, if you think about corn, if you go back to the Haber-Bosch reaction in the early 1900s, when they came up with the synthetic fertilizer, as soon as that started being applied routinely in US ag, for example, the need for nitrogen was being totally supplied synthetically. There was no driver, there was no pressure, evolutionary pressure or environmental pressure for microbes to do it. Matter of fact, it was actually removed in that process. So when you look at corn and wheat and some of these cereals, for some reason, they never had the opportunity to evolve with the nitrogen fixing microbe. There was never environmental pressure to drive that. And so today, if you look at the corn we have today, there is no magic microbe that you can put on as a seed treatment. There's no magic microbe you can associate with corn that will deliver nitrogen, will fix nitrogen from the air and deliver it to the plant like the microbes that are in the soybeans or peanuts or legumes in general.
So in this moonshot, is the moon landing, you have a microbe that can associate with corn, colonize with corn, and 100% replace all of the external fertilization needs for that corn plant?
Um, no, I'd say no. That's not for us. I would define the moon landing as us having a seed treatment or in-furrow product that a grower can put out there, and he can reduce his synthetic fertilizer use 40 to 50% and get the same yield or higher yield. So it's more of a Prius type approach as opposed to a Tesla. So at this point, we're not trying to go all the way to replace it 100%. We're not even sure that that's practical, but we think it would be transformative to agriculture to be able to show that you could reduce it 40 to 50%. That's a huge step. Now, where you go from there, we'll know better in 3 or 4 years, right? As the whole field sort of evolves and as people make progress. But for us, the moon landing would be, 40, 50% reduction in the input while maintaining the exact same yield or higher yield than what they're getting if they did a full 100% input of the synthetic fertilizer.
If you think about what's going on now out there with CRISPR-Cas, I've talked to several people who are involved in the food space, the prepared food space, who are using that technology to do really amazing things. One thing you said I thought was really interesting was, well, sometimes you can take these microbes and tweak them to say get that nitrogen production to really come in the second half of the corn's lifestyle. Is there any thought of looking at an existing legume, a soybean, that already has the fixation part that's solved, and just really dialing up the nitrogen fixation so it supplies, suddenly its roots are putting on 300 or 3x the nitrogen that it needs, 300 times as much nitrogen as it needs. So when that plant dies off, it got enough nitrogen to grow itself, but there's a huge abundance left in the ground for the next crop that follows it on. And in this whole corn soybean rotation that we have here in the US, a lot of farmers are planting corn after soy. Those soy roots are already there. They just, dissolve into the surface. Those nutrients become bioavailable. What about turning up the dial on current legumes to just produce more in an existing rotation?
It's a really interesting question, and I don't. In theory, it should be possible. I would say that from JOYN Bio's from our perspective, we focused our initial technical proof of concept and our initial research on working specifically with the corn itself and trying to get it to associate some of that nitrogen fixation with the corn. However, I would say, if you think about it, like you've said, if you could um, increase the amount of nitrogen production from a soybean, rhizobia. If you could increase it by 10 or 100x, and you leave behind in a rotational world, if you leave behind that much more, it's going to be complementary to, or that's going to be an incremental benefit to what you can do to reduce the synthetic fertilizer. Uh, and I would say, I'd say that's one of those ideas we have that we would look at sort of in phase 2 or phase 3 of our work. So I would, and we haven't done anything to date to explore it. I would just say that. So it's not something, but I think in theory it's absolutely possible. And the whole point of using these engineering techniques is you can take something very targeted, and if you understand the pathways and the genes and what they're doing, there's ways that you can optimize them for a very particular purpose, which may not happen in nature for 100 million years, but with the tools we have, by making these changes, you can suddenly make the change in a matter of months and years, as opposed to waiting for evolutionary pressures to drive it. It's just
Yeah.
really accelerating evolution when you think about it, right? Is the ability to go in there and have a very targeted output that you want, and then understanding the mechanics or the mechanisms of that microbe, and tweaking it so that you focus all its energy or all of its overexpression on that targeted output that you want.
Yeah, and it's being done everywhere. I mean, it's yogurt and a lot of other food products have this being done in wines. When you think about problem or challenge number 2 that you face, and that's public acceptance of this, how much legitimate worry is there that this goes Jurassic Park? You suddenly introduce these microbes into the soil biome that can now colonize with non-legumes, and there's 4 billion, some large amount of microbes in a tablespoon of soil, that you throw off that whole balance that's evolved to be there, and there's either unforeseen ripples, or it creates some sort of trickle down effect. Like, how do you even think about, when you drop that in the water, where the ripples go, given that immense complexity?
So I think the honest answer is that you don't know until you can do the testing. I think it's an important question that we have to answer. And when I was talking earlier about, if there's a big enough benefit to a new technology, to something novel that people haven't had before, that's really what drives it. That's what gets you in the door. But what actually gets you registered, or what actually allows you to be a product, is you're able to provide both regulatory agencies and the public with enough safety information that you can answer those type of questions. And so obviously, if we come up with a solution like that, one of the questions is going to be, well, okay, can you make, how long is it around? What's the persistence? Does it stay in the soil, or is it gone at the end of the season, type thing, right? And what impact, if any, is it having on any other microbes that are in there? And we're at this point, we've worked with native microbes for quite some time, and we've also done some work now with some of the engineered ones. We're compiling data that shows that those type of worst case effects or worst case outcomes, that's not what's happening. That's not the reality with what's going on with the microbes. But you can't just presume that. You actually have to go out and do the testing and be able to answer the questions to the satisfaction of the regulatory folks, and to a certain extent the consumer.
If you think about ways that these microbes could play out in terms of lifestyle or life cycle, one could be you inoculate the seed at the time the seed goes into the ground, or right before. It exists on the plant as long as the plant's alive. plant dies, microbe dies with it, and I mean total death, not dormancy, doesn't sporulate or anything like that. The other way would be it's like a normal legume. When the plant itself dies, the microbes go dormant in the cycle and dormant in the soil, and they'll stay there until the next legumes are planted or until they just can't live any longer. Would there be a desired outcome here when you're looking at colonizing some of these non legumes like corn? Is it associating with the plant while it's alive and then it's gone? Or I'm thinking from a farmer standpoint, you'd want these in the soil, like you inoculate, and you'd probably do it every time just to be safe. But why not have them survive in the soil if they could?
Yeah, I think it's obviously you can look at it you can look at it from both perspectives, right? I mean, if you're investing money in developing a new product, ideally, if you're the company producing the product, you want the grower to buy it every year, right? That's the economics of it. But I don't think in this case, I don't think it's black and white. I think that with time, if we can find microbes that do tend to stay in the soil, right? And so next year, when you come back, if you plant that corn, if there's a little extra there, it's an extra boost, and with time, it carries on. I think that's only a positive, because I think what the grower is going to be able to do then is go from a 40 or 50% reduction. Maybe they can go to 60, maybe they go to 70, right? You just keep incrementally ratcheting it up. So to me, I think you've got to remember that, what's the problem you're trying to solve for with all this, right? Where does the benefit of this come from? And it's a big part of it is from the fact that the synthetic fertilizers, while absolutely critical to today's food chain and today's food security and production, are not environmentally sustainable. Between the greenhouse gas emissions to produce it, so the Haber-Bosch reaction is very heavy in terms of the emissions that it does. So just producing the synthetic fertilizer attributes like 3% of the greenhouse gas emissions that are there. And then you also throw on the runoff, the impact of the runoff of the nitrogen, into groundwater and into the Gulf of Mexico and such. I mean, these are pretty well publicized environmental concerns. So if you just keep doing it, it's not environmentally sustainable. And yet today, you can't vilify it, because today it's absolutely crucial to the production of the food that we all need and want, whether it's for human consumption or animal consumption, right? So anything we can do, if you go back to what's the problem we're trying to solve, we're trying to reduce that synthetic fertilizer use to the smallest number we can. It both brings down the greenhouse gas emissions, and at the same time, it will have a significant reduction in the runoff.
I guess part of this also is you have to design this microbe to work in a synthetic fertilizer based environment where, traditional like legumes, mycorrhizal fungi, you provide too much nutrients, they shut down because the plant just says, well, I don't need this relationship. I can just go pull this out of the soil. If you want these microbes to stay associated with the plant, they almost need to turn a blind eye to what's there and just say, "Hey, we're needed later on down the line."
Exactly, exactly, and that's one of the engineering pieces that us and a few others are looking at, is what can you turn off or turn on to ensure that that microbe is not only fixing nitrogen, but also delivering it to the plant regardless of the environment it's in. I mean, you almost want it, you want it to do it in a nitrogen rich environment so that it's not turning off. And that's exactly one of the one of the sets of engineering approaches that we're taking.
When you think about the science of this, if you put rhizobia that associate with legumes in with corn, what exactly happens there? Is it just like they just don't communicate? They're just kind of there, both next to each other, and there's no reaching out by quote either party to try and form a relationship. Or and what triggers that? Do you have any idea in terms of your expertise? Is there a
I
chemical
I, per-
signal
I
that's
Yeah, no, it's a interesting question. I personally don't. I know that. I mean, I know people have done some work, and there that association and that is not there. And there's also because of the type of microbe that rhizobia is, it also its stability is totally dependent on that association with the soy root and the dynamics that evolved with, and you just don't have that on a you don't have that that whole infrastructure, if you will, that it has with a soy plant, with a corn plant. So as simple as it seems, just just transplant it. The attempts to do that, work that's been done on that, it doesn't work. What I don't personally know is the exact physiological reasons that are preventing that, or why that doesn't happen.
Right. So I'm imagining this corn is your control. Like that's where you start with, okay, we have this corn plant, we're not changing this. We got to get a microbe to go over and talk to this. What's there? Like what has to happen there for the microbe that you're designing to form that relationship with the corn? Is it the the microbe picks up on a chemical signal that the corn sends out? Like what I'm trying to get at is how does the microbe in the corn meet? How do they know, hey, there's something good here. We have to come together. Is it exudates? Like what brings them together and allows the corn plant to get the microbe to colonize it, to come inside of it?
Yeah, I think the short answer is it's related to signaling and to nutrients, or nutrients and metabolites that go back and forth between the two, that provide that attraction, whether it's a nutritional attraction, a signaling attraction, and going in both ways. The as we go all the way back to the beginning of our talk, I mean, the complexity out there, the billions of microbes out there, we're a long way from understanding exactly, and knowing exactly what microbes associate the best, and communicate the best, and have the best relationship with corn. What people are doing is going out and isolating microbes from corn plants in different geographies, and trying to classify endophytic spore formers, you classify microbes that specifically associate with the corn as a starting point, right? Because you rather than try to that would today that would be a very difficult thing to engineer in. We don't understand enough about exactly what all those dynamics are. But if we can start with a chassis or host that has already evolved, already has the properties that associate with that corn or that wheat plant, that's a great starting point. And that's sort of the power of what we're trying to do is find a chassis or host out there that already has that built in. And then can we optimize it, or can we engineer it to significantly increase the amount of nitrogen, not only that it's fixing, but also that it's delivering to the corn plant?
Yeah. How much do lab conditions vary over the wild? In other words, if you modify certain traits of the bacteria, like you said, they could exist in that container that's a lab, but now you put it out into the wild, all of a sudden there's other microbes out there. It has to have defense mechanisms. It has to just be able to survive on its own while it performs these additional functions. How much of a challenge is that?
It's huge. I think that's actually, I mean, I think it's one of the biggest hurdles. And I think um, if you look back, people have been working on biological solutions, microbial solutions, biological solutions for ag for 100 years, and really more recently for 30 or 40 years, right? And you sit there and say, wow, in a world where environmental sustainability is important, and in a world where clearly it seems like microbes should be you know a one of the solutions for growers. Why isn't the business bigger? Why aren't there more biological solutions out there? And why is the industry today totally dominated by traits and chemistry? And the reason is simple. It's performance. And the biggest knock on natural microbial solutions is consistency. They don't perform with the same consistency that traits and chemicals do. And one of the reasons for that is because they are living organisms. The products themselves are living. They're microbes, and they are impacted by the environment. And so temperature and moisture and all the things that affect a living organism tend to, as well as just the environment that they're put in, will affect their performance. If you think about a chemical, it for the most part, it doesn't really care. You spray that chemical out there and it kills the bug or it kills the disease. If you put a trait into a plant, it's relatively unaffected by what temperature the soil is, or how much moisture there is. It's actually in there. And so those are the tools that the growers have become very comfortable with, and they've become the standard from a performance standpoint. So how do you turn around? How do you take a microbe that is vulnerable or susceptible to the environmental conditions that isn't consistent? How do you get it so that it has the same level of performance as a chemical or a trait? And our belief is that you actually have to engineer, optimize that microbe and get it up above, get the performance up above the noise or the background that's there when you have a natural microbe, so that it is performing, even if the temperature goes down a little bit, or even if the moisture, all these things that might affect that microbe and its colonization, that you've now introduced it's now producing enough of the metabolite, or it's producing enough of the signal, or it's producing enough of the nitrogen that you are performing on a consistent basis.
Mm.
So it really speaks to, because we get why are you engineering? I mean, why not just go find a microbe that goes and does this? And the answer is people have been running down that path for 30 years. And there's arguably not a single blockbuster, there's no biological product that comes close to the use, revenue, success, whatever, of traits and chemicals. They dominate. And it's our belief is that from an environmental sustainability perspective, and just in terms of providing growers with tools that they're going to need to address climate change and regulatory change and consumer demand changes, and the whole food security piece, where are their new tools going to come from? Where's the innovation going to come from to allow them to withstand all these different all this adversity that's coming at them? And there will continue to be progress and solutions that come from traits. But the challenge there is you've got to do it pretty much one crop at a time, right? So, and by far the one that's had the most investment in it is corn, by Pioneer and Monsanto, now Bayer. A little bit with soy, but they're really just these big acre crops that have big returns that can justify a 10 to 14 year development cycle, right? So you've got to have a big crop for it. So where's it, but it's limited to just that. And then with chemicals, there's the number of new actives, the number of new modes of action, all of that has slowed down significantly across herbicides, fungicides, and insecticides. And at the same time, the regulatory pressure on it and on all those chemicals has been ratcheted up dramatically. So the door is open for these biological solutions. The door is there, but if you're going to go through it, you've got to go through it with products that perform close to or at the level that the existing products, that the chemicals and the traits do. That's the real challenge from a scientific from a scientific perspective.
And is the thought that the biology can do that? It's just engineering the biology in a way that it can consistently do that? Like, it's biologically possible. You guys are, and amongst other companies, have to just make a solution to take the biology and say, okay, it's going to work. We're going to make sure it works every single time, as stated.
Yep. It works every time. And, there's also, you can get into the details of rate. What rate does it have to go out at? So that, those growers can't be, and this is what I'm saying is, with a seed treatment, if you think about a seed treatment as a form of application, the amount of microbe you can put on that seed is limited, right? There's only so much space on a given seed for the seed treatment. So you've got to be able to have it be potent enough at some point. It has to be potent enough that it can work at in those small amounts. The same thing if you go out and put it in the soil, they're only going to put out a certain amount. So you also have to have a potency or an efficacy aspect to it, exactly how you described it. That microbe has been engineered for a very, very specific purpose, right? To maximize its production of a particular output or a particular metabolite to address the disease or address the pest, the insect, or in our case with biofertility, to address the nitrogen needs.
Are you aware of any microbes being used in agriculture that were engineered and they go out there and use today and they survive in the wild? Let alone forget making associations with plants, but are there biologicals being used that we currently make that they go out there, they're used no problem. So like the survivability problem could be conquered. Here's an example of it. The next step is okay, now it's got to associate with another plant to perform its function. But are there microbe products out there that are being used?
There's a few examples. I think the one I'm most familiar with when I was at Bayer was they had a seed treatment called Poncho Votivo 2. So the Votivo was a microbe that had in fact been engineered, and it provided both some level of nematicidal activity as well as sort of plant health, higher yield benefits to it. And when we went to register that, the nice thing with it was a good example where we, at that time, Bayer, we were able to go and register it via the states. So because it was more of a plant health type of a additive or a seed treatment, we were able to register it through the states specifically. And Bayer went to them and sat down with the state regulators, said, hey, it's engineered, here's what it is. And so it actually is a seed treatment that's used on a lot of the corn, or can be used on the corn. So that's a real example. It's a little different. The engineering that was done on that's a little different, it's a little different than the approach that JOYN's taking. But in fact, you ended up with a genetically modified microbe, and it was registered and it is being used. So it's one example. But there's very few. I mean, our approach to this and our joint venture with Ginkgo and having access to Ginkgo's synthetic biology tools and technology, this is really the first major attempt to do this in a big way, in a very directed way. So I think that those products are still to come.
In terms of that Bativa seed treatment, how was the efficacy of that compared to, say, just adding nitrogen fertilizer? If one of the targets was yield, how well did the biological work in terms of boosting yield, versus straight up untreated seed? I mean, was it huge? Like, is there a lot of potential here?
So the Bativa, it was, I would say, most of these seed treatments, most of these microbial solutions, and again, I'd say 99% of them are native. They're natural microbe solutions, right? But even the Votivo, the target there is can you consistently demonstrate a 3 to 5% yield increase over not using it, over a control? That was really the benchmark there. In our case, and this is what makes what we're doing a bit of a moonshot, is we're not we don't. It's not going to be very interesting. We're not going to land on the moon if we simply reduce the nitrogen input by 5%. Or even, frankly, if we have an engineered microbe that increases the yield by 5%, that's not going to, nobody's going to get excited about an engineered microbe if that's the limit of the benefit. The benefit has to be big. And if you look at, genetic successes or places where genetics have been genetic modification has been allowed, if you will. In Hawaii, they were going to lose all the papaya crop. So they allowed a genetic modification that protected that. The same thing's happening now with chestnuts. We're going to lose all of our chestnuts, but it is addressable with a genetic modification on it, right? So if you confront people with this, like something where the benefit is so big that you can't close your eyes to it, then I think people will at least give the GMO or the engineered microbe, they'll look at it, they'll give it a chance. But you can't be, if you're just down there playing with the same yield increases or the same benefits that natural microbes provide, then we won't have been successful. And frankly, why would you spend the time and money to engineer something if a natural microbe is just as good? It wouldn't make any sense.
Right. No, I get where you're coming from. It's fascinating where this is going, and I can already see parts of the public pushing back because it's different. You're engineering something. It's not natural. For people that might think that, what what are they missing? Maybe like what's the con argument to a lot of the anti-engineering of microbes that you hear? What part of the picture are they not seeing beyond the obvious benefit, but in terms of some of the potential dangers or repercussions? I think that's where people really get scared.
Yeah, I think I think there's a series of sort of scientific responses that you can give to that, but frankly, the public's not interested in scientific responses. So we could get into a discussion about, do you understand how often microbes are mutating all the time? All the microbes that are out there, the microbes on your skin, microbes in your gut, all that, right? These microbes are mutating randomly into things that we may not know what they do or don't do. And this is where some of the concern comes from, like disease, pandemics and these things is, are things changing out there, not from people doing it, but just natural mutation, natural evolution that's taking place. The benefit to what we're doing is we're doing it in a very controlled, totally known way. It's very directed. And once we do it, we also can test what happened and know exactly how it behaves, put it through all the safety tests. If it's happening naturally out there in the environment, you have no way of, nobody's monitoring that. So in some ways, by doing it this way, the argument would be you've introduced more control and you're able to do the testing to ensure that you're adding benefit but no harm. The problem with that is that kind of a science argument totally gets lost on the public. And what you have to do is come back with a more of an emotional type of discussion. And it really the story has to start and end with understanding the benefit. And an extreme example is insulin. Insulin for diabetics actually is made from a genetically modified microbe. But I will guarantee you that there's nobody who's diabetic even thinks about the fact that their insulin comes from an engineered microbe because it keeps them alive. I mean, it's just, right, nobody even questions that. Now, you could also make the argument, though, wait a minute, that's still in a contained environment. Nobody actually injected the engineered microbe into the diabetic. They actually just took the product. So, there is a difference there. And I would say for us, that's really the hurdle. That's one of the hurdles we've got to get over is can we convince people that moving these engineered microbes from a contained environment to out onto a corn seed or out into a wheat field, that that's okay? And the answer to that has to be science driven. We have to run the safety tests, do the studies, and answer everybody's questions. But it also, part of it will come in, well, why are you doing it? What problem are you solving? And if the problem you're solving is big enough, I believe it's in those situations that people will turn to new solutions or novel technologies that otherwise they might not be comfortable with.
Right. And I guess in the ag side, I mean, one approach is the no synthetic fertilizer side. And I get that approach and how some people make it work. On the other side, it's, well, what's going to do more harm, introducing these engineered microbes to the environment or continuing to pour the same amount of synthetic chemicals on the environment and having all the repercussions of that, both upstream and downstream, figuratively and literally. And you just got to say, which one are you more comfortable with? And I think a lot of this is just the unknown, right? Like people, it really, we're at a point now in science where a lot of our beliefs and like what even seems possible is being challenged. Like the whole idea of engineering a microbe to fix nitrogen for a corn plant and do most of that in the second half of the corn plant's life and then cease to exist when the corn plant dies. It's really sci-fi to a lot of people. And when you can't understand it, I mean, you have fear, and fear is a lot of times based on what's unknown. And this is a total unknown for a lot of people.
Yeah, I know it's a great point, and I think it's one of the things we've tried to think about early in this process is to not just focus on growers. So when we go out and talk to growers about this technology, and we go out to talk to growers about, okay, what percent reduction in nitrogen would get you excited economically? Because at the end of the day, for growers, you can talk all you want about environmental sustainability, but you also have to be able to talk about economic sustainability, right? And those growers are just trying to stay in business. They're trying to make a living, and it's getting harder and harder. So whatever solutions you bring them, they need to be economically sustainable as well as environmentally sustainable. And for us, when we went out and talked to them, that cutoff point's, somewhere around 25, 30% reduction. So once you get above 25, 30% reduction, the economics for that grower get really exciting, get really interesting. So from a profitability standpoint, which same as, being economically sustainable. And it's easy to focus on that. However, to your point, that's different than how the consumer looks at it. The grower and the consumer are two different entities. And I think if you look back on the history of GMOs, there was a huge focus on growers and little to no focus on consumers. And yet it was the consumers that have ended up being the ones who are the most distrustful or having the hardest time with, I would say, genetic engineering technology. And so we're really trying hard at this point to think about that and think about how to message and think about how to talk about it, not just with the grower, but also with the consumer. And again, you have to go into it recognizing, the probability that you're going to get every consumer comfortable with a new technology is zero. There's always, and it doesn't matter whether it's vaccine, you think about any technology out there, if it's new, there's going to be a percentage of people who, no matter how convincing it is, they're going to be skeptical or concerned, right? And so you have to set your sights on, you have to set your expectations on what you can and can't do there. So, but we're realistic about it, and it's certainly not a slam dunk. It's not a guarantee, but at the same time, we're so passionate about the potential that we think this approach has. And somebody's got to bring it out there for people to test and see and try. And if it really does work as well as we think it's going to, then we think there's a path to, with the right safety data packages, with the right studies, with the right answers to people's questions, we think there's a path, all the way to commercialization and actually making a difference in ag as a whole from a global perspective.
One of the terms that's came up a lot here is the technology that you're using to do this, synthetic biology. There's GMOs, there's CRISPR-Cas, which is gene editing, synthetic biology. How does that fit in, compare or contrast against GMOs and CRISPR-Cas?
I think it depends who you. I think it depends who you talk to. I mean, the it's actually an interesting name if you think about it. It's synthetic biology. The term would imply that you're synthesizing new life, right? That you're actually um, that the biology you have is synthetic, and I don't think that's really not what we're doing. We're actually using these engineering techniques that are evolving, and the technologies and the instrumentation and the software that allows this to happen at this molecular level, at the gene level. It's just remarkable now, using those tools for specific purposes. And it just happens that the the field adopted the name of synthetic biology. And if you look at some of the early pioneers there with Amyris and some of the early groups, they really pioneered this around biofuels, the whole drive for biofuels. And then that obviously collapsed. And so it required people to say, okay, it's really cool technology, but the commercial market went away. How do we reinvent ourselves? How do we, and what they've done in different models, whether it's Zymergen or Ginkgo or synthetic genomics or Amyris or all these, they've all reinvented themselves around slightly different business models, but aimed at how do these tools, how does this technology, this really cool technology, how can it apply to specialty chemicals? How does it apply to fragrances? How can it apply to bioremediation? How can it apply to food ingredients, right? And maybe one of the biggest ones, how does it apply to pharmaceutical and biotech uh, improvement? But they're all sort of based on this idea that microbes can do things that we can't do with synthetic chemistry. That's really the underlying, or that they can do things better and at a higher quality than what you can do with synthetic chemistry, or without chemistry, with a pure synthetic chemistry approach. And that's really the basis of it, is understanding and harnessing, from my view, harnessing the power of what nature's put into these little microbes, and harnessing it to produce metabolites or products or signal to plants in a way that a chemical can't. Totally different property from a chemical. And that's why I think ultimately in agriculture, you're going to see, 20 years from now, you're still going to see traits as a way to address some of the issues out there. You're going to still see chemicals, but I think you're going to have this whole new class of products or solutions that are based on optimized and engineered microbes that solve problems that the chemicals or traits can't, or complement in a very positive way and in an incremental way the problems that the chemicals and the traits are solving. And ultimately you've provided a whole new set of tools to the growers that are out there trying to feed the world.
So in a way, do you think we've gone as far as we can with chemicals? The upside there is limited. That curve's flattening out, and the microbial biological solution curve, like we're just taking off. That thing can just go exponential.
It's, if you, one argument, one way to look at that is if you go back over the last 10 or 15 years and you take the R&D budgets for all the big ag companies, and what percentage of that went to developing new chemical products or solutions. It's these R&D budgets these guys have are in the, hundreds of millions to billions, right? All focused on either trait in the case of Monsanto and Pioneer, and now now Bayer, or in the case of chemicals like Bayer and Syngenta and BSF, and it was Dow and DuPont, now it's Corteva. So just massive, massive R&D budgets, all on small molecule chemical type solutions. And you look at how much money was spent on developing microbial solutions. And 90% of it is all happening in these small venture capital based companies that are operating on R&D budgets of 5, 10, 15 million a year. I mean, and have for the last, right? So to me, it's not surprising that performance and consistency and the quality of trait and chemical solutions is up here. And down here, you've got the microbials, because it haven't had the investment, they haven't had the understanding or the technology applied to them. And at the same time, if you think about where we are as a scientific community, understanding the microbiome and how early it is, right? Because it's not, to me, it's just understanding a microbe isn't enough from an agricultural perspective. You also have to understand that microbe in a soil microbiome and in that plant microbe interaction, that plant microbiome. And our understanding of that it's such an early stage, right? That to me, it isn't surprising that you have the gap you have today between the two. Now, I think traits, I think there's some problem. I think there's certain things that's going to be ideal for, and that's going to continue to get the R&D spending. It's going to continue to try to solve problems in the big acre crops. I think that the chances that technology goes out to fruits and vegetables and all these other crops that are used to feed the world, I think that's going to take time because of cost and just sheer cost that it takes to do that. And with chemicals, you've got a regulatory challenge there, where the safety criteria and the safety bar has been raised so high, particularly from an environmental perspective, that to try to find chemical solutions that are so selective that the only insect that they affect is, this one, but it has no effect on fish and no effect on bees and no effect on anything else. That's a big challenge. And if you look back, if you go back in time, that selectivity factor, from my view, wasn't there. And should it be there? Absolutely, right? If you think about environmental protection, environmental sustainability, but you have to recognize that with that selectivity and with those safety hurdles, you're going to dramatically reduce the amount of chemicals out there that are going to get registered in all likelihood. And it's made it more expensive to bring a new chemical to market, because not only do you have to do all the environmental testing, but you've also got to look at all the human tox and, is there any chance it's carcinogenic? Well, okay, how long does that test take? How long do you test something before you decide that it's not carcinogenic? And you get into the complexity of it and the risk of it just keeps getting higher and higher because our standards get higher and higher.
So in the research you're doing with corn, is corn the lead domino here? Meaning, if you can solve corn and get a microbe to start associating with corn, fix nitrogen, that it will be, I'll say easier, not easy, but easier to then get one to associate with wheat or tomatoes or lettuce. But you got to do one before you can move on to all. Or do you see certain crops as just better candidates, not economically, but biologically?
So we're one of the key reasons we're focused on corn is the size of the market, the economics help justify it. So if you're going to go, if you're going to go, if Bayer and Ginkgo are going to go spend this money, they want it to be on something that where the benefit is unquestioned, right? If you can do it on corn, everybody gets that. So you've got to, when you're doing a moonshot, you're doing something like this, you've got to have a strong, you got to have a strong story behind it. And clearly, the other thing you want to do is you want to have the biggest impact environmentally. And so we could go solve this problem in, lettuce or cabbage or tomatoes. It's not even going to move the needle from an environmental impact point, which is part of what we're trying to show and part of what we're trying to do.
Well,
I
I mean, I get that part, but, like, let's say you did solve corn, and I get the whole big market side, and then you went on to the next biggest crop. Is it once you do it once, you understand enough to make it easier to do it again with another crop? Like, in other words, is the biggest hurdle the very first hurdle you have to go after, or do you think each one of these crops are gonna be equally as hard if you had to, look in the crystal ball and look ahead?
I, I think the first one, I think this first one with corn is absolutely the hardest one. And you think about, because we've got to be able to build all the assays to measure it. We've got to understand all the different key things we've done pathway wise. What I think will make other crops easier or make it go faster is that in parallel with the work we're doing right now, we have another whole program built around identifying chassis, hosts or chassis that are potentially ideal for other crops. So you may have you're going to have a set of you're going to have a handful of chassis that are particularly good for corn or corn-like plants. We also think that you're going to have chassis that are particularly good for other types of crops as well as for other geographies. So as you change geography, remember these are living organisms. Um, something that works really well in tropical climates may not work that well in North Dakota, and vice versa, right? So, and that's the beauty of being able to find these selected chassis or hosts. They can be selected for crop, they can be selected for selected for geography, and when they're selected for geography, there's two aspects to that. One is climate, but the other is registration. So, for example, if we want to go and register a new microbe, even an engineered microbe down in Brazil, one of the one of the most advantageous things we can have is to start with a microbe that's native from Brazil, right? They don't like new microbes coming in from that have never been in Brazil before. And the exact same thing's true in India, and the same thing's true in China. So in some of these other markets, bigger markets, if you can start with a microbe that's native to that country, your ability to go through the regulatory process is significantly enhanced. So this just comes back to this whole idea of building a library or a pool of these chassis, thinking about association with different crops, thinking about different geographies, and thinking about different geographies. And I think it really gets to your point, which is, is corn going to be the hardest one? Absolutely. And if we can get it to work in corn at 30-40%, and we understand why, and we've engineered that, then it's really a matter of finding hosts or chassis that have similar colonization, similar symbiotic relationships, just with other crops, that also could benefit from a nitrogen fixing microbe.
Do you think it's reasonably possible that this association between a non-legume and a nitrogen fixing bacteria has occurred in the wild? It's just nobody has been able to find it because maybe they're just not looking. Like, if you think about the trillions and trillions of microbes out there in the soil, mutating all the time, trillions and trillions of non-leguminous plants, you'd think at some point in time there has been some sort of mutation to make that cross. I mean, eventually it'll go back far enough in history, and that's how legumes came about. And is it the reason I ask is because it's to say, like, is it biologically possible? Again, you must think it is if you're going for it. But if you guys can recreate it, then nature probably did, but we just probably haven't been able to find it and isolate it.
Yeah, I think it's exactly right. I think either nature has and we haven't found it, or it will and we haven't given it enough time. And so then you'd step back and say, well, where should I go look? Well, you probably want to look in geographies or areas where people are trying to grow corn with little to no nitrogen, right? Where there's a night, where it's deprived, or so that and almost happening in a natural way, so that those pressures are there to drive that association or drive that evolution. So uh, do I think it's happened, that microbe might be out there? You could nobody could ever say it's not possible. If you think about the sheer numbers and complexity, and like you say, the mutations going on, finding that magic microbe, and thinking that and believing that, oh, that's the magic one to put on a corn plant, or that would associate with a corn plant. um, people have been searching for that for 50 years, right? I mean, it's
Yeah.
kind of holy grail, and they haven't been successful yet. um, could they? Probably. But even if they found one, I would still argue that our approach and our technology could make it better. And it goes back to your question, Diego, that you were asking earlier, is, could this same technology improve even more on legume, soy and peanut nitrogen production, so that it actually became a delivery mechanism into the soil, as opposed to just the yield or the production of that soy or peanut plant for that season. And I think you've got to believe, if you believe in this technology, the answer is absolutely. We could continue to engineer and optimize and enhance it. And it's would be another great use of this technology. People are talking now. One of the hot topics now is sequestering carbon, and the whole world. And there's a business world around that, but we also, when we're fantasizing, we also think about, wow, I wonder, is there a way that you could use microbes as a way to increase carbon sequestering, both around the roots of the plant or in the plant, as well as in the soil. And again, if you believe in this technology, and if you just let your head go, where could this go at some point? I think all those things they're still science fiction, but they certainly now, with the type where we're going with this stuff, they suddenly, it becomes a very different playing field than all I have to, the only microbes I can use are the ones that I find out there and isolate as natural microbes. You open up a whole new world from a design standpoint of what you can design that microbe, what you can optimize that microbe to do.
So really, and I mean, 50 years, it could essentially be anything. Water improvement, improving nutrient utilization, you know, isolating specific nutrients out of the minerals and rocks in the soil. Like, it's just really the world is the oyster here, and this is a whole new frontier when it comes to ag.
It is, and I'd like to think that some of the pioneering work we're going to do on the ag side will also spill over into some of these other fields. And I think but I think the one thing all of these different applications are going to have to find or have in common is they're going to have to find that chassis or host
Yeah.
works for that application. And I think that's one of the things that's so unique for um, applications like agriculture, bioremediation, applications like that, where the microbe, you're taking advantage of the fact that microbes do exist and can exist and even can thrive outside of a tank. They can do that in the environment. And so can we find ones that do that, either by their association with the plant or how much oil they chew up in a bioremediation sense? And can we harness and optimize that through engineering into a product that a grower or somebody can use commercially? So can we take it from an interesting science experiment, which is great, and that's your technical proof of concept. But for us, landing on the moon means that that product is in the hands of a grower, right? That he can use to produce food on a global basis. That's when you've landed on the moon. And if he can do it with half of the fertilizer that he originally needed, I mean, whether it's increasing production in the third world where they don't have access to synthetic fertilizer like we do in the US, or whether it's creating a more sustainable way to grow crops in the US by dramatically reducing what you do put out there, either one to me is a big transformative benefit to agriculture as a whole. Or certainly at this point, and we're careful at this point, you have to keep putting in the word potential. But until we've actually done it and have the rigorous field trial, rigorous science behind it, it's really just talking about it from a potential perspective.
To give people some idea of the scale or complexity that goes into this research, just identifying chassis to create this symbiotic relationship with corn, is it something where you're starting with a million potential choices and you got to narrow it down to 500? Like how, what does the funnel look like in terms of how much you have to sift through and how much you try and got to get it down to even go to the next stage?
Um, I, the way we're looking at it now, I think you start with thousands, in the thousands, not millions, so thousands, 1,000, 5,000, 10,000. Oh, but these would be microbes that already have sort of been pre-characterized in some way. And then when they come out of that funnel, maybe you're down to something more manageable, in that, let's say, 50 to 250 level, that you can then start to say, gee, how easy is it to engineer? How safe is, how stable is it? Some of these factors.
Mhm. And how long have you guys been working on this for so far to date?
This one probably, I guess, or fairly early on, maybe 6 months.
Okay, so 6 months on this, so early stage. And if you had
I
to
mean,
get,
yeah. So we've been working with some early chassis that we had, but it was as we worked with some of these early chassis, it sort of we recognized how critical it was, how critical the characterization of these of additional chassis was going to be. So we're really jump starting that and really focused in on that as a key part of our research right now. Because if you think about it, if you don't have chassis, if you don't have chassis that can colonize and associate with the plant as that delivery vehicle, um, the concept really it's hard to picture how the concept's going to work.
right, right. It's almost like those are your blank tapes or your DVDs, and okay, that's what you're starting with. You can write the content onto those.
They are, and it's novel because again, for the last 8 years, the synthetic biology community has focused on E. coli and yeast, and these, and so they're super well characterized. Everybody knows how to work with them, but they have to be done in a contained environment. So we go back to the beginning of our discussion. One of the big hurdles for us is, can we take synthetic biology and move it from a contained environment to a cornfield or an agricultural environment? That's a big jump, and you're only going to make that jump if you have chassis that have the characteristics like we've talked about.
Right. And so this now I'm more knowledgeable about this. If we go back to one of the earlier questions, I mean, one of the potential paths is you take a legume and you now get it to associate with corn. Well, that's doesn't sound like that's going to meet your chassis requirement because it doesn't have a pre-existing relationship with corn. if you had to do that, so you take something that works with soybeans and shift it over to corn, what's the factor there that you're fighting against? You got to get the corn to accept that.
You either have to get, yeah, you either have to find a association or a symbiosis there, right? I think at this stage of our knowledge, engineering that into, say, the rhizobia, into the soy microbe, that's really beyond our capabilities right now. To think you could change an organism or change a microbe to that level, that's a level of engineering that's, 5, 10, 15 years out. It's not the reality of what we have today.
It sounds like, I mean, like, we don't even know why the plant and that specific microbe talk to each other. So if you don't know the language that they're using to communicate, you can't set the speaker or the receiver on either side to actually communicate. Is that kind of a layman's way of thinking about it?
Yeah, I think it's just. I mean, I think we're just in the very very early days of starting to understand and see some of that. So I wouldn't say that we don't know anything. I think there are researchers, particularly in academia, who have identified signaling and stuff. We know some of the signaling that's going on, but compared to the whole picture and compared to what's going on, with hundreds, if not thousands and millions of microbes, it's very very early
Right.
days. What we do know for sure is that signaling and these communities are out there. They're real. We do know that there is a plant microbiome, and we know that plant microbiome and the soil microbiome together play play a significant role in the health and the productivity of that plant. What we don't fully understand is that we know that much, but how you can going in there and identifying if there's a handful of key drivers, if there's key signals and again, just when you think, oh, okay, I think I can zero in on this, you might be looking at a cornfield in Iowa, and does that even apply to a cornfield in Brazil? I mean, there's just this complexity. There's a complexity piece of it that's pretty daunting in terms of understanding agriculture at the individual plant level. So if you really want to like make your head spin, we talk about in human health, we talk about personalized medicine, right? Oh, and because each of our genomes is specific, we're going to develop a medical solution for each of us that's personalized to our DNA, to our genomics, right? So it's personalized medicine. Imagine if you had to think about that for agriculture and you're going to develop that personalized for each individual plant. And you just go, no, that's impossible. I mean, we work on thousands of acres and we work on hundreds and hundreds of greenhouses or whatever, but the idea that you would have something specific to that plant, yet that microenvironment that each of those plants is in, it is different. And each one is just like every person out there from a personalized medicine perspective is different. It's just that there's 3-4 billion people and there's quadrillions of microbes, so it's into the complexity piece of it and stuff. But so on one hand, it's really daunting and it's humbling to think about what an early stage we are in terms of uncovering this. And at the same time, it's super exciting to see where the tools to do this have evolved to in such a short time. If you go back 10 years, look at the cost of sequencing, look at the technology people were using. You fast forward to today, it's absolutely stunning, both on the instrument technology side and on the software algorithm computational biology side. And the learning, the learning tools that are there to do sort of, in Ginkgo language, to do like design, build, test, and keep doing iterations over and over and over again, looking to optimize, looking for these in the sense, uh, engineering biological samples the same way that an engineer was, doing computer code. It's just you've got four bases instead of on and off kind of thing, a zero and a one. But it's the idea is nature has programmed things at a level of complexity and that we can't even comprehend right now, right? It's just when we think about we program computers to do things, you look at what nature's programmed, and so tapping into that and starting to understand that and starting to be able to optimize it or do things in a highly selective way for a particular outcome, that's really the early stages that we're at right now. And the tools are going to get better, the knowledge is going to get better, but and at the same time the need for this innovation, the need for these products, the need for these solutions just keeps growing. And so that's we come into work every day, or well, we don't come into work as much as we used to, but but for the lab people coming in, that's really what's driving everybody, is the understanding just how important it is that we come up with some new biotech type tools that are going to help these growers and are going to help address all these different aspects of food production.
If you could look ahead, being 6 months into this, how long do you think you'd have to go into the future to see a nitrogen fixing microbe that associates with a corn plant? Forget the regulatory side, like something you could use on a test plot in the ground, in the wild. It's working. How far out is that? Is that 5 years? Is that 10 years? Where do you think we're at?
No, I think based on where we are today, I would say optimistically 2 to 3.
Wow.
And
So pretty close.
and then could it take 4 to 5? Sure. I mean, we're not, but we've made some pretty significant. We've made progress to date. We're getting a better and better understanding of not only what to do, but when we do those things, what kind of impact it has. So now we won't, which and to your point, there's a difference between having this work in a field trial and having a commercial product that's on every corn seed. Because in between those two things is you have to have adoption by Bayer and Pioneer, and because they control the corn seed, and you want it to go. Ideally, you want it to go on as that seed treatment. So realistically, even after you have something that works, they're going to test it a minimum of 2 years before they go and put it on everyone, all their corn seed. So there's always there's a delay there if you're going to go out as a seed treatment and you're going to go to market through Corteva and through Bayer. There's a built-in delay of a couple years, just because that's how the process works. They don't believe anybody's data but their own, rightfully so, and they're not going to jeopardize a multi-billion-dollar corn franchise, right, on something that they're not positive is going to work as well as they say it will. So if you tell growers they can cut their fertilizer by 40% and they go do it, and their yield goes down, that's not a good day. And so this gets back to sort of the consistency and the performance that we were talking about. When you play in the ag world, you've got, your products have to perform. They have to be reliable. They're going into an environment that is just loaded with risk. They don't know. They can't control weather. They can't control all these things. So the things they can control, like what products they use, they better work, and they better be reliable, and they better trust them. And so that's the environment you're selling into in the ag world. And so you have to accept that adoption goes fairly slowly, unless there's suddenly there's a crisis, right? If you're risked with losing a whole crop, if you're risked with, if everything's at stake, then you might adopt a little faster. Um, and so, if you fast forward 3-4 years and you're starting to see some serious regulatory pressure on growers in the Midwest on how much nitrogen they can use because it's getting into the groundwater or whatever, all of a sudden their incentive to look for alternatives goes up pretty dramatically. And that's certainly, I've always found it challenging to try to predict regulatory timelines. That's in any direction. So you have to be careful. But my point is, if when faced with something pretty dramatic, if somebody has a solution, your willingness to try something new is higher depending on, how big the crisis is or how big the challenge is.
Well, considering this has been, like you said, the holy grail of what a lot of people in ag have been looking for, to wait 5 years isn't that long term. Yet, just to close this out, I mean, one thing I'm curious of, as a business owner, you're CEO of a company where you're looking 5, 10 years into the future. A lot of businesses turn and burn, minimum viable product, like get something out there, sell it, let's keep churning through product. How do you approach a business, a project, looking at something that's so far out in the future and still be optimistic about it, still come in excited about it every day, still keep grinding in the face of failure when, one, it's a hard task, it's almost a seemingly impossible task to begin with, and two, it's gonna take a long time. And so many people listening to this, watching this, they have trouble taking on projects that are going to take more than 2 weeks. And here's one that might take a decade. How do you do that?
I think there's a couple pieces to it. One is I think myself and the team that I built, I think we've understood what the challenge was, and we knew what we were getting into when we started. So we were intentionally set up as a moonshot. We were set up with the idea that this was a big task, and we all kind of stepped into this knowing that this was high risk, and at the same time, if we're successful with it, it could have a dramatic impact. It could really be transformative, and that in itself is exciting. We also have expanded the portfolio of projects we're working on, so it's not just the nitrogen fixation, but we have some other pest and disease projects we're working on that probably could come to fruition, at least from a technical proof of concept, sooner. So we'll get some earlier successes to make sure we can show how well the technology works. And then I think scientists are always, when you're in these projects like this, you're always looking at getting to the next stage. If you go from, when you can go from an in vitro success to an in vivo and in planta success, and then you can go from a greenhouse success to a field success. I think we all understand that very, in these type of development programs, you don't go from 0 to 60 overnight. That that's what it's going to take. But what keeps you going is the state. Each of these steps that you're going up is in itself is a reward and gets exciting. So I think both of those, knowing that what we got into, and I think deep down in everybody, I think you're driven on a daily basis. You're also driven by how important the need is. The potential impact you can have and the need for it, and we all believe in microbes. We all believe in biotechnology and the genomics and the microbial engineering. And we're all pretty passionate about agriculture and how important it's going to be to the future of food security and food on a global basis to come up with some of these new solutions. I mean, I think it's pretty clear that the status quo is not going to get us there when we have 5, 6, 7 billion people. Yeah. So there's plenty of drivers and plenty of motivation, and it's if you love that intersection of science and business puzzles. Right now, I mean, ag's one of the funnest places to be. because it's there's very few things that have all the different pieces to it, and you've got to know the consumer, you got to know the grower, the science has to work, and you've got to make it work as a business. It's got to make sense as a business venture. So it's fun, and the team, I think the team is highly motivated. We've got two great parents supporting us in Bear and Ginkgo, and we'll see where it takes us. But we're at this point we're cautiously optimistic.
Well, it's a good place to be. And one final thought, what would you want growers, farmers to know about the future of agriculture from where you sit?
I guess I think to me um, maybe the most important thing to think about is speed. And I think what worries me right now, and what should worry people, is that an average new product in agriculture, whether it's a chemical product or a trait product, average development time is 10 to 12, 14 years. But with climate change and regulatory change and all that's happening that these growers are faced with, they can't wait 10, 12, 14 years for a new solution, because things will have already changed. So in the same way that people are looking at how fast we're developing vaccines for COVID, if you shift your mind and a problem becomes big enough, you find new ways to do things. That's the beauty of science, the beauty of innovation, the power of necessity, that you have to do it. And so I think, to me, a key lesson from this whole COVID thing is that we need to take into agriculture is thinking about how fast, as a scientific community, how are we going to be able to bring new solutions the same way these companies today are trying to bring vaccines in 1 to 2 years when it used to take 5 to 10? How do you think, and so I think agriculture as a whole needs to be thinking about that. And I think speed of development, speed of new products is going to be critical because of the rate that things are changing. And we're going to have to rethink how we do things if we're going to be able to give these growers solutions in a timely fashion. And I think it's one of the big learnings for me individually that's come out of this whole COVID thing, and watching how this whole race for vaccines has accelerated. And I mean, if you told people 2 years ago that you could develop a vaccine, even think about it, in 12 months, they would have laughed at you. But now they're trying. And whether it's going to be, in 12 months or 18 or 24, it's going to happen in all likelihood at a record pace. And that same mindset and approach, I think agriculture has got to be thinking about that, ideally before it's needed, not after.
Yeah, it's amazing, exciting times, and it's cool to get an inside look at it. So, Mike from JOYN, I want to thank you for coming on and sharing your thoughts today. I mean, it's been interesting on my part, but thanks again, man. Stay safe.
Oh, you too, and enjoyed the questions and the conversation, and really appreciate the opportunity to talk. So take care and be safe, and hopefully we'll talk again in the future.
Hi, everybody. Thanks for watching. Subscribe here to get the latest from the show. Also, be sure to check out some of the great clips and watch the full interviews right here on In Search